All right, let's finish up the Gram-Schmidt process in our ongoing quest for an orthonormal basis for a vector space. Gram-Schmidt process, stated as Theorem 6.4, the orthonormal basis theorem, maybe as well, says let W be a subspace of Rn, let A1 through A sub k be any basis for W, and let W sub j be the span of the first j of these vectors A1 through A sub k. W sub j is the span of A1, A2 through A sub j. So W sub j is a little subspace of W of dimension j. The claim is, then, there is an orthonormal basis Q1 through Q sub k for W such that each W sub j is spanned by Q1 through Q sub j. They've stated it like this because what they're doing is starting with any old ugly basis of W, and they're turning it into, and notice it's got k elements, a basis with k elements. They're turning it into a nice basis with k elements. By nice, I mean orthonormal. And along the way, by the way, they're picking up orthonormal bases for each of these little subspaces. So what we're going to do is start at W sub 1, having an orthonormal basis for it, moving on to W sub 2, a two-dimensional space, having an orthonormal basis. W3 will be a three-dimensional space with an orthonormal basis. And when we're done, when we reach k, j equals k, we'll have W sub k being a k-dimensional subspace of W. It'll be W itself. All right, so this is a bit of a recursive thing. And let's look at the proof, because the proof shows you how it works and how to use it. Okay, so it's recursive. And what we'll do is start out by choosing vector v sub 1 to be vector a sub 1. These subscripted v vectors are going to form an orthogonal basis, so we're just using those in passing. So v sub 1 is defined to be the first vector. Probably should point right there. That first vector in that basis for W. Now for j equals 2, 3, and so forth, recursively, let P sub j be the projection of A sub j onto W sub j minus 1, which will be the span of A1 through A sub j minus 1. That's as given. And let V sub j equal A sub j minus P sub j. This computation of V sub j is symbolically represented in a picture. So it's all geometry. This is the algebra in the linear algebra part, but it's really the geometry that will help you remember it. So this isn't so bizarre. It isn't complicated. It's tedious. You should be used to that by now. But whenever we say these projections, you know from the earlier stuff, those projections are computed using dot products. Okay, so here's the plan. Let's see, we got V sub j equals A sub j minus P sub j. Keep that in mind. And here's the little picture. We said V sub j equals A sub j minus P sub j. So what we've got is, at some point, we've created a j minus 1 dimensional subspace, and we're looking at the next, the jth basis vector, A sub j, and we're taking it and projecting it onto W sub j minus 1. Projections, think of them as shadows. So we're taking A sub j, projecting it onto this subspace down here, and then we know that A sub j, so we'll go through the proof, but A sub j can be written as its projection onto the subspace and its projection onto a perp space. So what we're doing is we're finding the P sub j and the V sub j, and those two are going to add together to give A sub j, with the constraint that P sub j lies in subspace W sub j minus 1. It's a projection. So what we're doing is projecting, subtracting, and producing something perpendicular. Notice this vector V sub j, as humble as this image is perpendicular to the subspace V sub j minus 1. V sub j is in the perp space of W sub j minus 1. Yeah, it's going to play a role in determining the space W sub j, the next subspace. Okay. P sub j is a projection of A sub j onto W sub j minus 1. So we know by some previous results and some definitions that A sub j can be uniquely written as projection onto W sub j minus 1. This is subscript W sub j minus 1 means we're projecting A sub j onto that subspace, and then we're projecting A sub j onto the perp space. We've taken A sub j and decomposed it into a component in W sub j and a component into W sub j minus 1, and a component in W sub j minus 1 perp. In the past, we used vector B, and we wrote B as its projection onto W plus its projection onto W perp. So we had a B sub W plus a B sub W perp. So this is the same stuff we had before, only with some subscripts thrown in and the letters modified slightly. So what we've got then is A sub j written as the projection onto the subspace, which we're denoting as P sub j, plus the stuff that's left over. Well, the stuff that's left over, either we compute it by finding bases, we've got a bunch of bases sitting around, or we just compute it by subtraction. We know P sub j, it's a projection. We know A sub j, it was given. So we can find V sub j simply by subtracting. We'll take A sub j, subtract P sub j off. You're left with V sub j. Hey, it's a, triangle. Whoops, I touched something. Triangle rule of addition. P sub j plus V sub j equals A sub j, or parallelogram law of addition. So we've got the summation, P sub j plus V sub j equals A sub j, or rearranging it, A sub j minus P sub j equals V sub j. All right, so big picture, took that new vector, projected it down onto the previous subspace, and got a vector in the perp space. Iterate that. Take this vector V sub j, use it to make vector space W sub j at some point, and then pick the next vector, A sub j plus 1. All right, project it onto W sub j, take a piece in the perp space, and repeat. By taking these V sub j's in the perp space, you're guaranteeing that you're getting an orthogonal basis. We were looking for an orthonormal basis, and we'll fix that at the end. All right, so we get A sub j written in terms of these projections. These are unique by some theory that we had earlier. V sub j is in V sub j minus 1 perp. It's perpendicular to everything in W sub j. So V sub j is perpendicular to all these vectors V1 through V sub j minus 1 that are in the previous space, the space W sub j minus 1. All right, so we're finding along the way orthogonal, not orthonormal, but orthogonal basis for W sub j minus 1. All the V's are perpendicular to each other by the recursive construction. And V1 through V sub j, orthogonal set of vectors. It's a subspace of W sub j. The dimension of W sub j is j. We said W sub j was a span of these vectors here. These were elements of a basis for W, but anyhow, they're still a linearly independent set, and they span W sub j. So these j vectors form a basis for W sub j, so j is dimension. W sub j is dimension j, as mentioned several times before. Now, we've got V1 through V sub j. Okay, these are orthogonal, and these are also a basis for W sub j. The theoretical reason is Theorem 6.2. We've got j linearly independent vectors in a space of dimension j. They must be a basis. That's what Theorem 6.2 said. You sure these V sub 1 through V sub j are linearly independent? Yeah, they're orthogonal. We built them that way. And orthogonal vectors are linearly independent. That was a big chunk of the argument in Theorem 6.2. All right, so we've created for each W sub j an orthogonal basis, V1 through V sub j. but we were looking for an orthonormal basis for all of those. Well, then normalize them. Take vector v sub I, divide it by its magnitude, do that for each of these j vectors. It's called the result q sub I. That's a notation in the theorem. And then we've got that W is the span of Q1 through W sub j. It should read W sub j is the span of Q1 through Q sub j. In particular, when j equals k, then we get all k of them is an orthonormal basis for W. All right, so good for you for sitting through the proof. Here's how we're going to use it. Maybe peek back up on the previous page. It's totally this idea about projections. We'll write it algorithmically here in a second. And let's get back to the notes. Okay, algorithmically, this is how the iteration works. To find an orthonormal basis for subspace W of Rn, first start with a basis. I don't think of it as a bad basis. I like orthonormal bases, and they've given us this bad basis. In practice, you'll be given a basis for the subspace and then asked to turn it into an orthonormal basis. You'll let V sub 1 equal A sub 1, like we did in the computations. Then you will, for the remaining indices, compute in succession the vector V sub j given by subtracting from A sub j its projection on the subspace generated by its predecessors. That was the W sub j minus 1 stuff. That produces a bunch of V sub j's that are orthogonal, normalize them, and there's the orthonormal basis. Computationally, what we're doing is starting with V sub 1 equals A sub 1, and then we're taking j equals 2. V sub 2 equals A sub 2 minus, we'll let j range from, I guess, 2 to 2, when we're doing V sub 2, A sub 1 minus. So no, I take it back. We'll have A sub 2 dot V sub 1 over V sub 1 dot V sub 1 times V. It's just a projection the first time around. Next, we'll move to the j equals 3. We'll take V sub 3 as A sub 3, and then we'll subtract off 2 pieces. Computationally, that's mostly what we'll do. You got more pieces, you do the same stuff. You got more A sub j's. You simply subtract off more expressions when you do the projections. Symbolically, that's fairly easy to write. You're just taking A sub j and subtracting its projection onto this little subspace here. This is W sub j minus 1. If you think about vectors as having magnitude and direction, this is all about the direction stuff. We're taking V sub 1 as the first direction. We're taking as V sub 2 the second vector minus the piece of the second vector that points in the direction of the first vector. So if we had two vectors like this, here's the first one, points in this direction, here's the second one, well, it's got a component in this direction. We're going to subtract that off and effectively bend up that second vector and make it perpendicular to the first one. You got another vector that appears, back off a little bit. Yeah, this other vector, if it isn't perpendicular, not perpendicular to the first two, you're going to bend it so that it is perpendicular, getting nice perpendicular V1, V2, and V3. They ain't all unit vectors. We'll fix that later. So it's very geometric, and think of it as taking vectors and throwing out components of them that point in directions you already have and using them for new directions. That's the idea of the Gram-Schmidt process. Oh, and finally, we'll normalize by taking those V's and dividing them by their magnitudes and produce unit vectors. Do that last, it simplifies the computations. Here's a little picture, let me make it bigger still, where we're taking this vector a sub 3 along with a vector a1 and a2 for simplicity. Let's let a1 point along the first axis, a2 point along the second axis, and a3 points out into space, as it were, as indicated by the dotted lines. What we're going to first do is take v1 to be this first vector. Then we're going to take vector a3 and project it onto v sub 1. Okay, there's how you take projections onto vectors with dot products, a3 dot v1 over v1 dot v1 times vector v1. That's how we did projections onto vectors before. Next, we'll take a3 and project it onto v sub 2. All right, here's the computation, but what that will give you in terms of the color pictures is, here's a3, it has a projection along this axis, given here. It has a projection along this axis, given here. First one in green, second one in blue. All right, so there's the projections of a sub 3 onto the subspace, which is the floor, the xy plane, if you like, in this three-dimensional coordinate system. And if we'll add the green vector and the blue vector, we'd get the little diagonal of this rectangle that lies in the xy plane. That's the projection of a sub 3 onto that two-dimensional plane. Subtract it from a sub 3. Well, that's going to leave you the part of a sub 3 that points upwards. Computationally, it's a3 minus this green part over here minus this blue part over here. Subtract from a sub 3 the green part and the blue part, and you should be left with the orange part. And notice it points straight up because it's supposed to be perpendicular to the subspace that's given by the xy plane when all the vectors are in standard position. Now the picture here that matters is green vector plus blue vector plus orange vector. Add those three together with a parallelogram law of addition and you'll get the red vector. They're at right angles. They determine a box, and A3 is its diagonal. Parallelogram law in 3 dimensions, really. Parallelogram law of addition. Okay, so let's do an example, number 10. But this is the formula that's going to make it tick. So we'll refer back to this. This is the formula you will use in computations. In your head, hopefully this is the geometry that you're thinking. I'm just taking a vector and subtracting off all the directions of that vector that have already been used, getting me a new direction. You also get a new direction because of the linear independence of those vectors. But conceptually, this is what you're doing. Computationally, and of course these are equal, this is what we'll be doing. All right, so let's look at that number 10 from the supplements. Okay, and these you need to practice. They're, you know, a bunch of computations. It's just an algorithm that you'll follow. All right, so 3 vectors. We'll probably denote them. I see it in the shadows. We'll denote them as A1, A2, and A3. They say this is a basis for R3. They want us to transform it into an orthonormal basis. Okay. These vectors orthogonal? No, you take dot products, you ain't getting zeros between any pair of them. We're going to fix that and get 3 vectors that are perpendicular to each other, and we'll turn them into unit vectors in the last step. All right, so first, let these vectors be A1, A2, and A3, because that's the notation we had above. We'll let V sub 1 be the first of those vectors. Done, we got the first vector. Hasn't been normalized yet, but we got the first vector in an orthogonal collection. All right, next, as I was trying to say before, let's find V sub 2 by taking A sub 2 and subtracting its projection onto all previous vectors. Well, they ain't but one, the V sub 1. Let's go ahead and look at the next one. When we do V sub 3, we'll take A sub 3 and subtract its projection on the direction of V sub 1 and in the direction of V sub 2. So I have to subtract 2 things off here, 1 thing off here. If we kept going, we don't have to because there's only 3 vectors. We'd subtract 3 things off next and so forth. So this could take a while to do by hand. But in terms of what we're looking for V sub 2, this is the computation to do. So it's just a matter of substituting and doing the arithmetic. Second vector, 1, 0, 1. Okay, so we're taking the second vector and subtracting the projection of it onto the first vector, v sub 1. All right, that'd be 1, 0, 1 dot. V sub 1 is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. You run around the little curve there with the v sub 1s. And then we have the v sub 1 vector. Do the dot products, do the arithmetic, and apparently it produces this vector here. So here's the vector v sub 2. Now, v sub 3 is found by taking the next vector in the original list, 0, 1, 1, the a sub 3 vector, projecting it onto v sub 1, here's v sub 1, and then projecting it onto v sub 2, here's v sub 2, and then subtracting away. Computationally, here you go. So straightforward stuff. Of course, the kind of thing you'd need to practice to put the routine deeper in your skull. And we do the arithmetic, and what do we get? I guess we get this vector here. All right. So we found a V1, a V1, a V2, and a V3, three vectors that are orthogonal. Here they are in the numerators of what we've got going on here. So 1, 1, 1, 1/3, 1, -2, 1, 1/2, -1, 0, 1. All right, so that's the three vectors we had above. Now we're going to take those and divide them by their magnitudes. We're going to normalize them. I guarantee you these three vectors are orthogonal. All right, then all we got to do is normalize them, divide them by their magnitudes. Here's where the messy numbers will certainly, almost certainly come in. We're going to make these unit vectors. You're probably going to see square roots when you do this. So magnitude of this vector is 1 squared plus 1 squared plus 1 squared square root of, leads us to a square root of 3. Okay, now we've got a unit vector. It's parallel to this vector with the same direction, in fact. Take the magnitude of 1/3 times 1, -2, 1. Apparently it gives you out 6. Square root of, and so we divide by the square root of 6 in each of those, divide by the appropriate thing over here. Here's the three vectors. Maybe we didn't divide by the square root of 6. There's a 1/3 that's playing a role here as well. But normalize the vectors, and there you go. Now you've got three orthogonal unit vectors. You have an orthonormal basis for that subspace. So it was R3. We've got an orthonormal basis for R3. I can think of other orthonormal bases for R3, but they wanted us to apply the Gram-Schmidt process to the collection of vectors they gave us. And there you go. So that happened fast because I just clicked through it, but it was just dot products and arithmetic. Dot products and arithmetic done in a very specific way. So here's the answer. Let's wrap that up with something a little more clean, saying we usually express bases as sets. Here's an orthonormal basis. The Q1, Q2, Q3 is a set. So there's an orthonormal basis for R3, resulting from applying the Gram-Schmidt process to these three vectors here. Let's see what's next. Okay, QR factorization is next. Let's put that on hold for a little while. I'll exclude that from this video. Let's concentrate on the Gram-Schmidt stuff. Okay, back, I guess in section 2.3, we saw, somewhere in chapter 2, we saw that every set of independent vectors can be expanded to a basis for Rn. You take independent vectors, linearly independent vectors from Rn, they can be expanded to a basis. We're going to say the same thing holds if you want an orthogonal basis or an orthonormal basis. So if we start with an orthonormal set of vectors in Rn, it can be enlarged to a basis of Rn. And that's exactly what the statement is. Every orthogonal set of vectors in a subspace W of Rn can be expanded, if necessary, to an orthogonal basis of W. Okay, so I guess they left orthonormal out. We could put normal in there as well. But every set of orthogonal vectors from Rn can be expanded to a basis of, so doing a basis of subspace W. All right, that with what we know isn't hard to establish. We know a bunch of stuff by now. Okay, so here's what we're going to do. Oops, QR factorization. We ain't going to do that. So we hop over this QR factorization stuff for now. Okay, here we go. Okay. So take V1 through V sub R to be that set of vectors in the subspace W that are orthogonal. So we got V1 through V sub R. There's a set of R orthogonal vectors. We know they're an independent set, linearly independent set. Orthogonal vectors form a linearly independent set, Theorem 6.2. We know by Theorem 2.3, I guess it was, that we can expand that into a basis of W. We've got linearly independent set of vectors can be expanded into a basis. Okay, so take V1 through V sub R, add those vectors that can be added to create a basis of W. All right, the claim is it can be expanded into an orthogonal basis. Here we've extended it into a basis. I don't know if it's orthogonal or not because I don't have any handle on anything about these new vectors that have been added. Subscripted A's is suggestive of some recent stuff we did though. All right, here's what we're going to do. Let's apply the Gram-Schmidt process to this basis of W and create an orthogonal basis. We'll just leave off the last step where we normalize, and if these were normal vectors, we could carry this over to an orthonormal system as well, but we'll do what they say. All right, so apply the Gram-Schmidt process to this collection of vectors. All right, when you take V sub 1 equals V sub 1, you're good to go. When you take V sub 2 equals, you take V sub 2 and subtract the projection of it onto V sub 1, there ain't a projection. All these are already orthogonal. When you did that subtracting of the projection, you were creating an orthogonal set of vectors. Well, the first R of them are already orthogonal. That was given. But the last bunch of them, maybe not. All right. So what's going to happen is we'll apply the Gram-Schmidt process. Nothing will change for V1 through V sub R. For the rest of them, though, stuff will probably change. You're going to take A sub 1, project it onto the subspace, subtract that, and create V sub R plus 1, and so forth. So what we'll end up with by the Gram-Schmidt process is an orthogonal basis if we don't normalize, and it includes those first R vectors. They won't change through the Gram-Schmidt process. These other ones will likely change. But the claim was, take these vectors, extend them to a basis, orthogonal basis, starting with orthogonal vectors. Done. Gram-Schmidt process won't change these unless I want to normalize, so don't do that to answer this question. It does change these, and we'll replace them with vectors that are orthogonal to each other and all the other vectors. That is, it'll replace them with an orthogonal set of vectors given an orthogonal basis for this subspace. Gram-Schmidt process creates orthogonal bases, better yet, orthonormal bases. Okay, I think next is some examples. I want to do the first one and the last one. The other stuff is either QR factorization or stuff I'll leave it to you to read. Let's look at number 20. Okay. They say, find an orthonormal basis for R3 that contains this vector. By the way, I've seen that vector before. That popped up when we illustrated the Gram-Schmidt process before. It's a unit vector for sure. Okay. Well, this is a little different. Gram-Schmidt process takes a basis and makes it an orthonormal basis. Well, I tell you what, let's do. Let's take the given vector and let's add the standard basis vectors to it and create a set. All right. Does this set span R3? Yeah, because the three new vectors that we added span R3. They're the standard basis vectors for R3. We've got 4 vectors from a 3-dimensional space. You know there's some linear dependence by, I guess, Theorem 2.2, relative sizes of spanning and independent sets, way back in chapter 2. Okay. Well, I tell you what, let's pick out in order which ones are linearly independent. I know there's linear dependence. I want to see which form a basis. We did that by taking the components of those vectors, creating columns. Remember back when we put vectors in a matrix as columns? This is how we found independent sets back when. And we'd row reduce and look for pivots. You find a pivot-free column, you found a vector you don't need. Throw it out, and the remaining vectors form a basis for whatever span that you were talking about. We dealt with this initially in the setting of column spaces, I think it was. Was it row spaces? Dimensions are the same, you know, the rank of the matrix. But we can keep 3 of these. We've set that up with those vectors as columns, do the row reduction. Third column is pivot free, so you can throw that third vector out. It is some linear combination of the first 3. You want to find that linear combination, we can do that too. But all we want to do is throw one of them out. It looks like this one goes. And that's probably highly dependent on the fact that we listed it last, that it went in this process. Unless you have the 0 vector in the first column, you will get through the Gauss-Jordan elimination, you'll get a pivot in the first column. If we got rid of the first vector, then that's a bad thing because they wanted an orthonormal basis that contains the first vector. Okay, so we've got linear dependence. We can throw out that that vector to keep the first 3. So, throw out that 0, 0, 1 vector. It's already gone. And keep the first vector, the second vector, and the third vector in that previous set. So A1, A2, A3, they're linearly independent. There's 3 of them. We're in R3, so they form a basis for R3. Now let's Gram-Schmidt and convert that into an orthonormal basis. Okay, we'll let V1 equal A1. There you go, done. We'll let V2 equal A2 minus the projection of A2 onto V1. Okay, projections are calculated in terms of these dot products. This is a formula you need in your head because that's how you calculate projections, and that comes up over and over and over and over in the Gram-Schmidt process. So we'll substitute in A2, which is what, 1, 0, 0, there it is. V1, it carries this 1 over square root of 3 with it, sorry. So here's V1 dot V1, and here's vector V1 outside. At least the square root of 3's, looks like they all cancel. And we're left with, after some arithmetic, this vector. There's your vector V sub 2. I'll guarantee you it's orthogonal to V sub 1. We made it that way. It's not a unit vector. We'll fix that later. And they wanted an orthonormal, I think, in their statement. Okay, so now we got V1 and V2. Let's find V3 by taking the third vector and subtracting the projection of that vector in the direction V1 and subtracting the direction of that vector in V2, leaving a vector V3 that will be perpendicular to both V1 and V2, creating a third direction in a sense. We've got the V1 direction, the V2 direction, and the V3 direction. And those are mutually orthogonal. We made them that way. They're not unit vectors, but we'll fix that at the end. Okay, these projections, bunch of dot products, square roots floating around in that first part, just like in the computation of V sub 2. There was a 1/3 in V sub 2, so there's 1/3s all over the place as well. Do the arithmetic, when all the dust settles, we end up with this vector as V sub 3. So that V1, V2, V3, there's an orthogonal basis for R3. We want to go one step further. We want an orthonormal basis. So we'll normalize those vectors, call the result Q1, Q2, Q3. Vector V1 was already a unit vector, so normalizing it is dividing it by its magnitude, dividing it by 1, so nothing changes there. We'll keep that first vector as is. Here's the second vector. We'll compute its magnitude. In fact, we have upstairs, I think. Compute its magnitude, divide by the magnitude, produces this. Yeah, I expect to see square roots when we do this normalizing thing. So that's one reason to save it until the end. And then we'll take Q3, divide it by its magnitude, and produce Q1, Q2, Q3. Here's the 3 vectors that form an orthonormal basis for R3. that includes that vector given. So a little more discussion about this. They said find an orthonormal basis for R3 that contains this vector. There you go, previous slide. Now, we took that vector and we threw in the standard basis, ejected one of those, and then applied the Gram-Schmidt process. Okay, well, we could have listed those three in a different order. That'd probably change things. We could have taken a different basis of R3. That would have probably changed things. There's a bunch of potential different answers for this. We found one of them, so that I'm happy with. And one final example, zoom ahead through this stuff. Let's look at applying the Gram-Schmidt process in, if we've covered this, in an inner product space. Okay, back in the inner product spaces, remember we denoted inner products with the angled brackets. We often had functions and integrals that express these inner products. So we're taking as our vector space the span of 1x and x squared, where we're restricting x to be between -1 and 1. So we're getting what's this polynomials of degree at most 2 defined on the interval -1 to 1. They bracketed that off in order to create the inner product. And then we're defining the inner product as an integral from -1 to 1 of f of x, that vector, times g of x, that vector. This is back when, somewhere in chapter 3, where we were taking vectors as functions. Many of the more advanced applications of this stuff, the vectors aren't arrows, they're functions. So magnitude and direction becomes a bit fuzzier if I've got vectors that aren't just arrows, like they are in Rn. They're something else. Okay, well, geez, if we've got inner products and projections are defined in terms of inner products, all we got to do is take our Gram-Schmidt process and replace the dot products that we used in Rn with the inner products that we're using here. They gave us 3 vectors. Let's call them A1, A2, A3, because that's what we did in the Gram-Schmidt process. We'll let V1 equal A1 equals 1. Then we'll take V2 to be A2 minus the projection onto V1 of A2, which is computed in terms of this inner product. This was quotient of dot products it was, now it's quotient of inner products. The inner products are computed in terms of integrals, so that produces these 2 integrals. A2 is x, there's the x. V1 is 1, there's the 1. Inner product of 1 with itself, inner product of V1 with itself. Okay, so these are the computations to be done. Perform those computations, easy integrals, these are just polynomials. And when all the dust settles, it looks like we get out x. So we took x and subtracted 0 from it. What that tells you is those 2 vectors, the first 2, they were already perpendicular. That's why they didn't change. Of course, the first one doesn't change, but that's why the second one's the same. And finally, for V sub 3, we need A sub 3 minus the projection of A3 on V1 and minus the projection of A3 onto V2. We'll express it in terms of the inner products. The inner products are integrals. All right, so it's the same stuff over and over. It looks more complicated because we got inner products that are expressed as integrals instead of just straight up dot products, but it's the same thing. Take those inner products, here you go. We were subtracting a projection onto V1 and a projection onto V2. That's what these are, written in terms of the inner products as integrals. Evaluate those integrals. Looks like we end up subtracting 1/3 this time. So we get for the vectors, we had 1, x, and this, V1, V2, and V3. All right, we'll take 1, x, and this, and normalize them to complete the Gram-Schmidt process. So we'll take 1, find its norm. You might think the norm of 1 is 1. It's not, because of the way the inner product is defined. It's actually square root of 2. Take 1 and integrate it from -1 to 1, and then take a square root. That's how you compute norms in an inner product space. So anyhow, we get 1 over the square root of 2. We get x divided by. We'll evaluate that. It looks like a square root of 2/3 pops up. Here's q sub 2. Similarly for q sub 3, we'll go through. normalize it. And I can see this taking a lot of time if they gave us any more than this, producing some scalar multiple. And now that Q1, Q2, Q3, these are orthogonal. V1, V2, V3 were orthogonal. We made them that way with projections. And these are also unit vectors. That is, these Q1 through Q3, this is an orthonormal basis for that vector space span of 1x and x2. With respect to this inner product, the inner product induces a norm. These are indeed unit vectors. So that ought to be a nice healthy dose of the Gram-Schmidt process. So there we go. Have a nice day. I'll see you in QR factorization, and then we'll finally wrap up this section. Have a nice day.